Good day. My name is Vedant Kandalkar, and this presentation on deep learning is part of my branch, which is Electronics and Telecommunication Engineering. Through this project, I've had the opportunity to dive deep into the architecture of neural networks and even apply them to solve problems. I'll be walking you through that I've learned and the fascinating potential of this technology. My activities on pre-trained models and fine-tuning, which is guided by Professor Sailis Adiman. What are pre-trained models? Pre-trained models are neural networks that have been previously trained on vast amounts of data for a general task. This initial training allows them to learn fundamental patterns, features, and representations that are broadly applicable across various related problems. Features like reduced training time, improved performance, effective transfer learning. Popular examples are BERT, which is Google's model for natural language understanding, excellence in sentiment analysis and question answering, GPT, OpenAI's series for natural language generation, NLG, capable of writing coherent text, translation, and summarization, ResNet, a deep convolutional neural network architecture primarily used for highly accurate image recognitions and tasks. All these are based on pre-trained models because these models are already trained by a huge amount of data, which is help, helpful for improved performance. Why pre-trained models matter? Training cutting-edge AI models from the ground up is an undertaking of immense scale, demanding staggering computational resources and expertise. This is precisely why pre-trained models have become indispensable. Extreme resource demand, acceleration development, increased accessibility, and enhanced performance. These are all features of pre-trained models. Now, what is fine-tuning? Fine-tuning refines a pre-trained model for targeted tasks, selectively updating its parameter, either partially or fully. As a core technique in transfer learning, it transfers broad knowledge gained from large-scale training to new specialized domains. This approach shines with limited data, requires far less compute to achieve superior results, ideal for practical applications where datasets are small but valuable. Unlock efficiency. Achieve high accuracy with datasets as small as thousands of examples. It means this data has lots of amount of uh, information or data which is huge comparatively to thousands of examples. Fine-tuning workflow step by step. Select pre-trained model. Choose a base model suited to your domain, like ResNet 50 for computer vision task or BERT for natural language processing. Ensure alignment with your input data type. Second, modify architecture. Adapt the model as needed, such as swapping the final classification layer to match your target classes or adding custom heads for regression outputs. Third, freeze and unfreeze layers. Unlock only layers to retain general features like shapes and textures, while allowing higher layers to adjust for task-specific nuances. Fourth, train on custom data. Optimize weights using your datasets with your with lower rate, monitoring validation metrics to refine accuracy and overfitting. This is visual representation, visualizing fine tuning image classification. Example, a pre-trained model like one trained on ImageNet excels at recognizing broad object categories through learned visual hierarchies. Fine-tuning tailors it to niche domains such as distinguishing breeds of dogs or styles of furniture by adjusting the subtle differences in your labeled images. The payoff models achieve 90% plus accuracy using just 10% of data required for scratch training, slashing time from months to days. The efficiency transforms prototyping into production-ready solution. Now, this is visual representation of fine-tuning, where low-level features are edges, corners, and textures. Mid-level patterns are parts and motifs. General categories are dog, chairs, and vehicles. Specialized classes like chair types, hot dogs, and fine-tuned outputs are domain-specific levels. Advanced techniques, parameter-efficient fine-tuning, adapter modules, techniques like LoRa, low-rank adaptation, insert lightweight trainable adapters to the model, present 99% of parameters, minimize updates while preserving core knowledge. Cost saving. This method cut memory by used by up to 3x and training time by 10x compared to full fine-tuning enabled deployment on edge devices without performance trade-offs. Key applications essential for scaling giants like GPT series or stable diffusion, where full retraining is impartial adapters maintain near equivalent results with fractions of the resources. Real world impact, business and industry use cases, healthcare. In healthcare, fine tuned models enhance diagnostic precision for rare diseases using scar MRI scans, improving accuracy by 20 to 30% over generic systems and accelerating patients' outcome. Finance. Now, in finance, custom models detect institution, institution specific fraud patterns in our transaction data, reducing false positive and saving millions in potential losses through adaptive anomaly detection. Now, in customer service, how customer service is linked with fine tuning. Chatbots refined on company dialogues, deliver personalized check-aware responses, boosting satisfaction scores. Example, DMC Chat GPT 3.5. Fine-tune automates mortgage approvals, cutting processing by 50%. Challenges and best practices. First, combat overfitting. On small datasets, apply drop-out data augmentation and early stopping rigorously validate to ensure generalization beyond training example. Layer selection. Experiment with phrasing ratios, deeper phrases for similar tasks, partial for divergent ones to balance adaptation, speed and feature retention. Hyperparameter optimization. Tune learning rates. Start low, example 1:5, and each batch size carefully. Use schedulers to generate adjust for stable convergence. Enhance robustness. Blend pre-trained and fine tune weights via interpolation. Mitigate domain shifts, preserving reliability across varied inputs. Tools and resources for fine tuning today. Hugging Face Transformers library with Trainer API. Simply NLP fine tuning with just a few lines of code. Handling tokenization and evaluation seamlessly. PyTorch and TensorFlow offer extensive tutorials for vision and multimodal tasks, including pre-built pipelines for transformer learning. Hubs like Hugging Face Model Hub and TensorFlow Hub host thousands of ready to fine tune models paired with open database glue, example glue for text, and libraries like datasets for effortless preparation. Now the future of fine tuning in deep learning. Parameter efficient methods like adapters will dominate, enabling fine-tuning of trillion parameters models on consumer hardware. Expect deeper integration with reinforcement in learning and RLFH HF for adaptive human-aligned systems. This evolution democratizes AI, empowering startups and researchers to innovate without massive infrastructure. Fine-tuning bridges the gap between cutting-edge research and practical deployment. Your next breakthrough awaits with a single pre-trained model. Embrace fine-tuning, the key to scalable AI innovation. So this was my activity and this was my presentation. Thank you for